Hello, this presentation is about an ECG design designed in Biomedical Engineering 462, Medical Instrumentation at the University of Wisconsin-Madison, and this project was done by Alyssa Aker and Nick Gilling on November 18th, 2015.
So the motivation for this project includes that ECGs are very important in monitoring the overall health of a patient's heart. For example, about 2.2 million Americans experience atrial fibrillation in their lifetime. And also from observing these waveforms, we can detect basic irregularities in the ECG, such as bradycardia and tachycardia, which we'll look at further in this lab.
The overall goal of an ECG is to show the QRS wave, which is the biopotential of the heart. In this project, we'll be taking in voltages at leads 1 and lead 2, shown on the diagram in the bottom right, and calculating lead 3 and formulating the QRS wave. So the overall procedure of this ECG design goes as follows. We start off by designing the ECG schematic using PSPICE software and testing Bode plots and gains and outputs and such. Next, we designed the PCB using Eagle software and soldered on each of the parts individually. We programmed the Arduino for data collection and configuration, and then we designed LabVIEW code for data analysis and observation. And finally, we tested our ECG.
So now we'll look into our Arduino code a little bit. We'll just give a quick rundown here, but the rest of the code, or the full code, will be available at the appendix of our report. We begin the code by setting up serial communication between the Arduino and the serial monitor, shown here with serial.begin. Then we read the data in from each of our electrocardiogram leads using the analog read function, so lead 1 and lead 2. We then look at the values in our check saturation function, which simply looks to see if they are saturated values or not, meaning they are 5 volts. And then we print those values out to our serial monitor, which goes to LabVIEW. So next we'll look at our LabVIEW code.
So here is our VI for our ECG that takes in data and does some processing. This VI consists of 2 sub-VIs, one here which does simple lead calculations by taking in lead 1 and lead 2 as inputs and calculates lead 3 and some other variables. The other sub-VI is implementing the Pan-Tompkins algorithm and does some data processing, which is what we'll talk about in a little bit. This whole top right corner here is a circular buffer that takes in data and does peak detection so that we can determine the BPM of the patient. It also gives feedback to the patient as to whether their BPM is in a current state of tachycardia or bradycardia, or if the BPM is normal.
Okay, so now we'll show you the setup to our ECG. Here is the ECG itself with the Arduino underneath. Right here we have the driven right leg input, and right here is the audio jack, which contains the 3 other leads, or excuse me, the 3 other electrodes which make lead 1 and lead 2. And now here's Alyssa to demonstrate putting the leads on. First she'll put on her driven right leg to her right leg. Now she'll put on the right arm lead, the left arm, and the left leg. And then now that we're all set up, we can go into LabVIEW and make sure we're set up, and then we can start to record our data. Okay, so here we're showing the first stage of our output from the ECG. Right here we have lead 1 graph, and right here we have a lead 2 graph. So these are just the raw signals. In our Pan-Tompkins sub-VI, we have a few additional output graphs. Again, we just have the raw signal here. And then here is actually the output from the bandpass filter from the Pan-Tompkins sub-VI. Here, the output moves into a derivative function, so we can start to find where our peaks are in our QRS wave to determine our heartbeat. So we'll find the derivative, and then we'll square that derivative here on this graph. And then we're going to take the average with an FIR filter and play that, or display that in this graph here. So that with the threshold peak here is what determines our heart rate, which is shown here in beats per minute. And this display here simply lights up for each heartbeat. And then moving over here, we have our lead calculation sub-VI. So again, we have our lead 1 and lead 2 raw data, and then after which we calculate our lead 3, which is simply lead 2 minus lead 1, as well as some other output data. Yeah. Yeah.
When the patient's heart rate is below normal levels or extremely low, the patient will be in bradycardia, which is demonstrated here. Here we are demonstrating motion artifacts, so when the patient is squeezing their fists, you can see that the LabVIEW code or the circuit is responding to that change.